So welcome to this first lesson on the hyperbola. We've so far had a look at, in this section, around graphs and equations of the circle, and we've done the ellipse. We're going to come back to the parabola. We're going to do the hyperbola for now. And obviously we've been touching on Cartesian and parametric forms, and I've been looking at some of the properties, focus directrix properties, those sorts of things. What's the eccentricity? We brought that in with the ellipse. Directrices, foci, all those sorts of things. Okay, so let's move on and just let's have a look at the hyperbola then. So if we start with our idea about conics, we start with a cone. We've already seen the circle, that horizontal section of the cone. We've seen the ellipse, which is that sloping section of the cone, but one that doesn't go parallel to the cone's edge itself. And then the hyperbola is what we get when we cut straight down. Okay, so we cut straight down through, and we hit something in the top and we hit something in the bottom. That gives us a hyperbola. Hyperbolas do occur in the real world a lot. So you think about the orbits of comets can be approximated this way. You've got sonic booms. Looking at this here, the sonic boom, the shock wave that's coming out of there, you end up with a portion of a hyperbola that gets traced out on the ground by that shock wave. See them in ancient Grecian pillars, and if you've ever seen sort of a coal-fired power station and had a look at a power station cooling tower, that's a hyperbola as well. That shape is hyperbolic. Okay. So one of the things we looked at when we looked at the ellipse was this idea that if we added up the distance to each focus, the total never changed at any point on the ellipse. It was always the same. Remember that piece of string, and we could move it around. That piece of string, same length, move it around, you get an ellipse. The thing with a hyperbola is that you get the difference between the distances as a constant. So let me just bring up my pointer. My laser pointer. So if I think about the distance from the point P to this focus over here, and then subtract away the distance to that focus there, I always get a constant. It's always the same thing. The magnitude of the distances are always a constant, okay? Because obviously in some cases, if I come over here, this part is going to have its distance to G further than its distance to F, okay? But if we look at the absolute value of that distance, that would give us a constant. Okay, let's drop that off the pointer. So here's a hyperbola, the standard form of a hyperbola. This should look quite similar to what we had for the ellipse. The only difference being we've got a minus here rather than a plus. Okay, we had a plus between the x squared over a squared and y squared over b squared, but everything else is exactly the same. The one on the other side, that is the form of a hyperbola. So, okay, it's looking similar. Remember that the ellipse looked similar to a circle, and again we're getting the hyperbola. The form of that looks very similar as well to the ellipse. Okay, we get 2 points here. These points here are called the vertices, where the hyperbola crosses the x-axis in this case. We have a hyperbola here where a is greater than b. If b was greater than a, it would look the other way around. So it would have its intercepts on the y-axis rather than having intercepts on the x-axis. Okay, so we generally look at it this way around, but we can also look at it the other way around as well, where the intercepts will be on the y-axis. Again, like we did with the ellipse, we more often than not had the major axis running along the x-axis, but sometimes the major axis ran along the y-axis. So same sort of ideas going on here. These dotted lines in here are asymptotes. So asymptotes being lines that a curve gets closer and closer to, approximates closer and closer to, but never actually crosses. And they can be really useful in helping us to sketch a hyperbola. If we know where the asymptotes are, and we've got where these two vertices are, we can quickly and easily sketch the hyperbola. Okay, so we're going to spend a little bit of time having a look at that today. So if we move on from that, there's the vertices we've got labelled. Okay, difference to the ellipse equation, we've already covered that. We've seen the difference to the ellipse equation is that there's that minus in there rather than a plus. Parametric equations. Now, in terms of our standard, the parametric equations aren't all that important. They are equally important as they are for the ellipse, generally, if we're going to study conic sections, but for our internal, they're not too important. But we could express them in terms of trigonometric functions as well. Sec, remember, is the reciprocal of cosine, and we've got tan coming in there as well. So we had sine and cos before with the circle, which is the special case of the ellipse, and also the ellipse. Here we've got sec and tan. We move on a little bit from there. Our asymptotes, we can see, are given by y equals plus or minus b over a. B over a being the fraction. If we come back to our form of the hyperbola, we can easily identify what b is, because that's b squared on the bottom. We can easily identify what a is, because that's a squared on the bottom. So we can easily write this. Y is plus or minus b over a x. Okay, so we get the gradient is b over a here, and here the gradient is minus b over a, and they both pass through the center of the hyperbola, in this case the origin. How do we determine that? Well, if we just have a think about it a little bit, okay, if we said, first of all, thinking about how we get the vertices, well, that's quite easy. If y is 0, just putting y is 0 in there gives us x squared over a squared is 1. So x is plus or minus a. That's fine. If with the asymptotes, if we think about x tending to infinity, so x gets really, really, really big. Well, as x gets really, really, really big, y is getting really, really big as well. It's going to go the same way, because we've got this expression here that effectively we could rearrange in it and say that y squared over b squared is x squared over a squared minus 1. That 1 becomes less and less significant as x gets bigger and bigger and bigger. And we can see that as x is getting bigger and bigger, it must mean that the y is getting bigger and bigger and bigger as well. But because this 1 is getting less and less important, okay, we can effectively say that y squared over b squared is approximately x squared over a squared. All right, these two things are getting bigger and bigger. The 1 is less and less significant. These are heading off to infinity. So we get x squared over a squared is approximately y squared over b squared. Okay, and that gives us this thing that we got here, plus or minus. Okay, bringing up the b squared here to go with the x squared. Y squared is b squared. X squared over a squared. Square root it, you're going to get the plus or minus. Okay, so we get that bit. We've talked about this bit already as well. If we swap the axes round, so the hyperbola would intercept the y-axis and not the x-axis. The only thing that would be different, really, is we would have in that case these things taking the other way around. So you would have y squared minus y squared over b squared and x squared over a squared being subtracted the other way around, just in the same way. Okay, the y is taking the place of the x. Well, that was coming first. The x is taking the place of the y. That was coming first. Okay, and the thing that's with the b there is going to be determining now where we're going to be crossing on the y-axis. Okay, the b squareds give us the b's here. All right. Okay, so just swap round. All right, let's have a go at sketching a few, see how we get on. So if we're looking at 9x squared minus 4y squared is 36, we're going to have to divide through by the 36 first. We've got to get it looking in the standard form. Okay, it's got to be equal to 1. Just as we had with the ellipse, it's got to be equal to 1. So we'd have to do that division first. Then we can easily see we've got x squared over 4 and y squared over 9 is 1. A is 2, b is 3. We've got our asymptotes. Okay, the asymptotes are plus or minus, y is plus or minus 3 over 2x, and we know our vertices are going to be at 2, 0, and minus 2, 0, because we've got the a value. So from that point, it shouldn't be too difficult to sketch it. Okay, we can put those in, sketch our asymptotes in, put in where the vertices are, and we've got a nice little sketch going on there. So if we were to, let's start and take that back off. If we were to start working through these bit by bit, and if you want to have a go at these, by all means pause the video at this stage, have a go at all three if you want to do that, see what the vertices would be, see what the equations of the asymptotes would be, see if you can get a nice little sketch going. So if you do want to pause at this point and have a look, see if you could do those three, then we'll leave that right now. Press pause, have a go. Okay, so let's start coming back through these ones. This first one, we're going to have to divide by 16, aren't we? So we'd end up with x squared over 16. Actually, what I'm going to do, well, I'm going to do this one, if I change my pointer options, and I just go for a little pen, I should be able to sketch these on the side. So we're going to get x squared over 16, and then the 4y squared over 16 would just become y squared over 4. and that equals 1. Okay, so at that point, we should be able to see that a is the square root of 16, b is the square root of 4. So in this one, we've got a is 4 and b is 2. So when we look at what this one's going to look like, let's move him on. So we're going to get, 4 minus 4 and 0 at the vertices. The equations of the asymptotes, so remember that's plus or minus b over a. So 2 over 4 is going to give us a half, so it's going to be plus or minus half x. And then I'll sketch with those two vertices marked on and the asymptotes sketched in. Something like that, perfectly good. Okay, next one, we're going to have to divide through by 100, aren't we? Because we need to get that down. So I'm going to get x squared over 25 over here is going to be minus y squared, following on from that, over 4 is 1, dividing through by the 100. So again, I've got the a value quite easily. It's the square root of 25, so that's 5. And I've got the b value quite easily. It's the same as it was before, it's 2. So we know that our vertices now should be at plus or minus 5 and 0. So we'll reveal that. We should know our asymptotes are going to be at plus or minus 2/5 of x for y. And then we've got our sketch going through those 2 points, those 2 vertices, and we've got the asymptotes. Last one is already nicely in the standard form for us, but we've got this number 8 and this number 2 here, which are a little bit more difficult to work with because they don't square root, do they? If I square root 8, this will give me the a value, so let's just do that. Square root of 8, I'm going to leave this as a nice square root because remember 8 is 4 times 2. 4 is a square number, remember that's why I want to do this, just so I can simplify it out a bit nicer. So I can take that 4 outside the square root, a is 2 root 2. Okay, that comes out nicely. And b is just straight away root 2. I'm not going to be able to do anything with that. B is just straight away root 2. Okay, so we're going to have, again, our vertices are going to be at plus or minus 2 root 2 and 0. On our asymptotes, if we do b over a, the root 2's cancel. Yeah, if you think about that, the b over a, the root 2's will cancel because there's one on the top and one on the bottom. So I'll just get plus or minus half x. So step him through. I'll do points, plus or minus half x, and then I'll sketch. Right, so hopefully that was okay. You did well with those. Hopefully you did have a go at them as well, not just let us work on through them, have a bit of a think about them for yourselves, but you can see how those ones build up. And I do encourage you to pause the video at times and have a go at stuff. If I suggest you do that, it's a good idea for you to have a go. All right, let's move on. So let's have a look at this hyperbola. So like we did a little bit with ellipses, things can shift at times. So if you think about how this hyperbola is going to look compared with the one where we're not doing anything inside the squares, okay, we're subtracting 2 before we do the x part squared, and we're adding 3 before we do anything with the y bit being squared. So what's going to happen, do you think? Have a think. So hopefully you realize this is just the same as what would happen with the ellipse. The center is going to move. Okay, our center was at the origin. Our center is now going to move to the point 2 minus 3. Okay, that's the only thing that's going to happen. But otherwise, that hyperbola would have exactly the same shape. Yes, the asymptotes are going to move along with that too. So rather than your asymptotes going through the origin, you're going to have to think about those moving along too. And that might, you might have to think a little bit about that in terms of getting the sketch. But actually the gradients of those lines, if you think about it, because the shape has just moved along, the gradients of those lines will not change. They will be exactly the same as they were previously. So where we were getting the plus or minus b over ax, we're still going to have the plus or minus b over a. Okay, that gradient is still going to be the same. But where we had x, we're going to have to replace that with x minus 2. And where we had y, we're going to have to replace that with the y plus 3. Because that's what we've done here. We've replaced the x by x minus 2 and the y by y minus 3. So just to sort of exhibit that a little bit more. So the equations of the asymptotes, if we just take, if I just take the first one, the positive one. So I just put y plus 3 is the b over a part. B here is obviously 4 square root of 16. And the a is 5 square root of 25. And instead of the x, I'm going to have to put brackets around it here because this is the x was all being multiplied by 4 over 5. So the x is now all having that 2 subtracted off it. Remember, this is the centre. We got the centre up here, didn't we? That the centre was going to be 2 and negative 3. You can kind of see that in there, that's your centre. Okay, and your asymptotes are going to, well, asymptotes are going to be really badly drawn, but they're going to come up and down like that. And you're going to get the same sort of thing going on, very badly drawn. Oh, couldn't even hit the point. But you get the idea. What's happening there? They're going through those points. You can then deal with that. So this is what we've got here. Let's just deal with it. So what's that really telling me? It's telling me that the equation is y plus 3, if I like, is 4/5 of x. Yeah. And minus 2 lots of 4/5 will be minus 8/5. But I like to see the equations in the y equals form a lot of the time. It's a nice way to do it. So I'm going to have to subtract 3 off both sides as well to get what y equals. 3 is 15/5. So I'm going to get 4 over 5. I'm going to subtract away another 15/5 for the 3 to get that out right. So that's going to be 23 over 5. Okay, and you would have to do something similar for the negative one. Be careful, you can't just say, oh, I'll just make that plus or minus there, because this minus 23 over 5 will not be the same. Okay, it's not going to be the same. Think about it. This bit on the end here is the intercept, isn't it, of the line. So I'll come back up. I lost my pointer for a second. Let me just see where I am. Come on, pointer. All right, let me just click. That's helped. Right. So if I come back up here, I can see one of them is going to have an intercept about there, and one of them is going to have an intercept about here, isn't it? They are different values. So this thing on the end will be different because you'll have had a minus 4/5 times a minus 2 rather than a 4/5 times a minus 2. Okay, so just be careful on that if you're asked to do those bits. All right. So that really is the end of lesson 1 for the moment. Okay, so we've got this new form, this form for a standard form of a hyperbola. The parametrics, I don't want us to worry about too much. Yeah, okay, if we're going to do this in complete detail, we would be looking at that as well, but the way it falls with our trigonometry as well, sec and tan, are really not things that we've spent a lot of time looking at the minute, and they're not key for this internal. And the equations for the asymptotes, we just discussed that as well. Okay, the vertices being at those points there. The form you've got drawn on the left-hand side there is just a form that's showing you what it looks like if it's centered the origin, isn't it? Okay, so this is the form when it's centered the origin. Obviously, these points would move as well if we were doing this kind of thing. All right, so you'd have to think about how they translated along, and the intercepts and so on are going to change, but they would still be the vertices. Okay, the vertex would move h along and k up in each case. Okay, so there ends the lesson, a bit of talking. There'll be some questions coming up if you want to dive into the classroom and have a look at Dr. Frost. Some questions to have a go at there, see how you get on, and I'll see you next time.